Great, so wait for that. I'm Ted Wilcox here from NASA Goddard. I'm in Code 561, which is our flight data systems and radiation effects branch. So I am very much a hardware guy, not a Linux kernel developer or anything of the sort. What I wanted to speak about today is a little bit more on the hardware side and some of the implications of the natural space environment down to our device performance. So we'll provide a little bit of background on radiation effects at the piece part level, all the way up through systems, and describe some of the effects on a functioning system as a result of the interactions with the ionizing radiation environment present in space. I will be in the no slide template purgatory here for a bit, but we'll get that squared away eventually. And then all of these slides will be uploaded to the NASA NTRS website. They're in the release process that we always do prior to giving a talk. So you'll be able to access all of these through nasa.gov, as well as whatever the distribution is from this session. So there's three sections to this talk. One is a sort of a primer background on the space radiation environment itself, types of particles we have to deal with, and when you should be concerned about it. We'll describe the basic effects on electronic parts systems. And then some of the recent test results from my testing and our organization's testing, the most common behaviors we see and some of the implications for system behavior. So I'm going to go from the universe down to the transistor here in a couple of slides. We have three big drivers of radiation effects on our electronic systems in space. And these are the big drivers of space weather, space climatology. And those are the sun, the Van Allen belts, and galactic cosmic rays. So when we talk about the sun, we have background activity and we have solar particle events, coronal mass ejection, solar flares, and the sun's activity is really driven by the 11-year solar cycle you're probably familiar with to some degree. Right now, we are approaching or about at the solar maximum level on the most recent solar cycle. So far, it's been a very active cycle. During those peaks of solar max, we see increased coronal mass activity, lots of frequent solar flares. We see a lot of particles, a lot of X-rays coming off the sun. We also, all the time, we have the trapped particles in those Van Allen belts. And then while there's a fluctuation, these are persistent background levels. This is the primary driver of our dose absorbed in our electronics for emission in low Earth orbit, medium Earth orbit, and high Earth orbit to some degree. There are some nuances to this, to the arrangement of the Earth's magnetic dipole that I'll get into, I believe, on the next slide here. And then we also have this persistent galactic cosmic ray background. These are the relativistic particles. Some of them are, well, the majority are protons, but there are also so much heavier ions. And these are really the most potentially destructive particles we see in the environment. And they really drive a lot of our survivability and reliability requirements from a radiation standpoint. These originate from outside of the solar system. A lot of these are supernova driven. And some of the origins are still under active investigation to figure out where exactly these particles originate. I don't expect you to be able to see a whole lot in this chart, but I just wanted to get through some of the characterizations of solar particle events. These are a lot of the events that will really drive the effects on computational systems. So NOAA defines the solar particle events into 5 categories from S1 through S5. Just to real briefly give you the range, S1 is talking about very minor impacts. You might see a few bit flips in your data system, something like that. And S5 is things like the collapse of the power grid. A very bad day, particularly terrestrially, but really for our satellite systems. So we see a lot of implications here for communications, for global positioning satellite systems, for weather satellites, for aircraft navigation being interrupted. So all of these have varying probabilities during one solar cycle, but of course the most severe are pretty rare. These tend to happen once or less per solar cycle. I mentioned that the Earth's magnetic field is not a perfectly symmetric dipole. So we have something called the South Atlantic Anomaly, that some of you may have heard of. What this means is that we have an area in South America and into the South Atlantic where there is an increased prevalence of protons trapped in the proton belts of the Van Allen belts. And so what happens is the Van Allen belt comes down to a lower altitude just above the South Atlantic. On the left, we see what that looks like from a modeling standpoint. So this would be a common modeling tool we would use to show the density of trapped protons at a particular altitude over the Earth's surface. And on the right is sort of the proof that it's a real thing and not just imaginary. This is Sampex data. It's 30 years old, but it's upsets in an SRAM-based data recorder. And we can see that there's a whole lot of them happening in the South Atlantic area. This is a real effect with real implications on a lot of our missions, including the Hubble Space Telescope, which has real operational changes based on passing through the South Atlantic anomaly. Question? Yes.
Is there any change from the climate change warming up in the oceans and things like that that's going to adjust to that, do you think, or not?
Boy, I wouldn't think so,
Okay.
but that's an interesting thought.
How about if the poles split?
I don't know. There are a lot of folks here at NASA Goddard that work on heliophysics and the fields from a scientific standpoint that are much more knowledgeable about the physics of this than I am, certainly more the applied hardware level. But all interesting questions.
The poles split, we might have hear problems.
Well, we go back to, these solar particle events. What does it really matter if you have a few glitches in your GPS if your power grid is down? Some of these have some pretty significant potential effects. They go far beyond Linux operating satellites. So I want to talk a little bit about the effects sort of at the transistor level, and then we'll work our way up as we go through the presentation. So very broadly speaking, so first of all, quad E parts is the new triple E parts, which was electrical, electronic, and electromechanical, and now we have electro-optical. So we keep building our acronym here at NASA. But we've got gradual degradation effects. These are things like total ionizing dose and displacement damage dose, which is similar to total non-ionizing dose, excuse me. This is what we talked about when we refer to a mission ending early because of radiation, something that was damaged or did not survive long enough during its mission. This is a premature wear out type of effect on our devices. But then we also have sudden failure effects, single event latch up, single event gate rupture, single event burnout. These are effects that happen because of one particle striking a transistor that's operated just a particular way at just the right moment, can cause our device to completely fail or burn out. And then we have the transient anomalies. These are the recoverable glitches, the data bit flip or analog glitch in your output voltage. Single event upsets, transients, functional interrupts. There's a whole acronym soup that we can go into here. And we'll talk about each one of these in just a little bit to set the stage. One of the first questions I'm asked working on a project is, hey, what are the KRADs? Well, okay, it's not quite that simple. But when we talk about emissions total ionizing dose, we are talking about a quantity measured in rad or gray, depending on whether you are American or the rest of the world. A gray is 100 rad, just for reference here. This is a result of energetic photons and charged particles interacting with the mass with any mass really, but in particular our electronic system. So generally we're talking about silicon and silicon dioxide within a semiconductor material. This is, again, a long-term accumulated effect. It is life limiting. So from a practical standpoint, some of the effects we see here are increased leakage current at the transistor level. We see gains reduced, maybe in our bipolar transistors. We have voltage regulators that now drift from what they are supposed to be outputting. Non-volatile memories that are unable to erase. High-speed CMOS logic that has a slower propagation delay than it did before. Data converters that now have an offset in your readout analog voltage or the digital value. Dark current in our image sensors is potentially a big problem for some of our telescope missions here at Goddard. Oscillators that shift frequency, darkening in optical materials like windows or LEDs, and complex devices that just suddenly fail because of all of the above happening within a black box. So it is our job to figure out all of these effects and make sure they don't bring our mission to a premature end. There are some mitigations that are pretty common here. From a dose standpoint, we're talking about shielding. Dose is a first order shieldable. Sometimes we are changing our parts out and finding a part that is rated or can be tested to survive the dose environment. Sometimes we are making design changes to tolerate those parametric shifts or changing our operations. So maybe we're turning off when we pass through the South Atlantic anomaly, so our devices are not biased when they're receiving the dose, which can have an effect on some of our absorption of the dose and the parametric changes. And sometimes we're employing sparing and redundancy. If we know the devices will not degrade the same when they are turned off, we can have redundant copies of parts, systems, and assemblies. But then single event effects is potentially the bigger challenge, I think. This is the more interesting part of the field to me. This is what we see from day one of a mission. And it's certainly much harder with complex modern systems to build something that is entirely SEE immune. So we're increasingly talking about being resilient, reliable, and tolerating these effects. So single event effects are instantaneous or transient. They are caused by a single particle, maybe a proton or anything up to typically an iron atom that strikes a particular sensitive portion of an electronic device. So I'm talking about at the transistor level, oxides, depletion regions, that sort of thing. As the particle passes through a material, creates an electron hole track, an ion track through the device. So now we have free carriers that are generated in the semiconductor material. These will be attracted to different portions of the transistor and collect charge. At the end of the day, that means voltage in a place where there shouldn't be voltage. This can also be caused by protons that collide with our semiconductor material. These are more nuclear effects. So now we have secondary fission fragments that come off, and they can add even more complexity to this. It's called indirect ionization. But ultimately, the results here, talked about a couple slides before, are either destructive or non-destructive, and those have very different ways that we have to handle them. Yeah, so consequences. As you can imagine by the name, destructive is a little bit different than our non-destructive effects here. A destructive SEE is something that's capable of ending the mission on day 1 or day 1000 if they're random. The 3 most common types of destructive SEE that we see are single event latch-up, which is a possible vulnerability in any CMOS device. See gate rupture and burnout, a little more applicable to power MOSFETs. So we see this in our power electronics a lot. And the destructive SEE are things that we want to avoid. We want to pick parts, technologies that are immune or have been tested to show that they are not susceptible. These are challenging to mitigate and very difficult to predict a priori, meaning if you hand me one ADC and another ADC, analog digital converter, and you say which one of these will be susceptible to signal latch-up, I can't necessarily tell you without doing a test. We also have our non-destructive effects here. These are data corruption, glitches on the outputs, resets of a computer. These are complex. These are hard to fix with design. They are usually not solvable by part selection. I can't simply pick one processor and say this will not have non-destructive SEE versus this one that does. These are complex. They are things that we want to tolerate. We want to accept them because we want the high performance capabilities of modern devices, but we have to figure out a way to operate through it. That's where we get into mitigation, tolerance, and sometimes we ignore them. MEAL is mission, environment, application, and lifetime. It's a common term we use here at least. And really what that's saying is you have to understand what your circumstances are and understand whether you can tolerate these effects or you have to get rid of them completely. Just a couple of pictures here on the bottom. We see some destructive effects. Let's see, is my cursor. On the left here, we have actual cross sections and SEM imagery of 2 devices that were subject to destructive SEE during testing. And so you can see very physical destructive effects that have happened to some of our power. I believe those are power Schottky diodes, actually. These streaks here, this matrix looking thing, is a 3D visualization of, it's a 2D projection of single event upsets in a 3D NAND flash. So vertical is actually depth in the material. So the streaks you see are actually single particles passing through the multiple layers of the 3D memory. And then on the right, it's a little hard to see, especially those of you that are farther away in the room. But there are a couple streaks. These are single event functional interrupts in a software-defined radio, causing streaks to appear persistently in an image that's being transmitted. In terms of mitigation here, I already kind of talked about avoiding the destructive SEE is certainly plan A. We really talked about that in terms of part selection concerns, but sometimes it is about operating a part within a safe operating area. For non-destructive, I already talked about characterizing and mitigating these. So that is usually something like a filter for an analog effect or redundancy, error detection and correction on your memories, watchdog timers to recover from an event that does occur, power limiting to try to make some of these destructive effects not so destructive, independent power cycling so we can turn off something and turn it back on again if we have to without bringing the whole spacecraft down. We really want to identify those risks and explore the consequences. So when we do our testing here, just show a couple pictures to kind of break up the words. These are parts that have been prepared for single event effects testing. When we do this, we go to domestic cyclotron facilities. So we will sometimes take anything from a transistor level up to a single board computer and put it in front of a cyclotron and see what the effects are of the ionizing radiation. At most of our domestic facilities, the energy is such that we can't penetrate the lid of the device. So we tend to delid the devices. We are operating at much lower energies than those galactic cosmic rays, which will not be bothered at all by the lid, but this is sort of a test prep phase. But it means we end up removing the lids on, let's see here, we've got, this is, I believe it's a Kintex 7 FPGA. In the upper center here, we have some power transistors. Upper right, these are PIC microcontrollers. Lower left is a NAND flash, and then this is a radiation hardened FPGA at the bottom. And then I mentioned some of those facilities. Left side there is the NASA Space Radiation Lab, which is part of the Brookhaven National Lab on Long Island. That is the facility I was at most recently over the summer. Other common facilities, we have the Lawrence Berkeley National Labs. This is a DOE facility. These two. Bottom is Texas A&M, so they're university facilities. This is actually a really nice facility to do SCE testing. Okay. And then really the newest entrants to this field are some of the medical proton therapy facilities. So in the upper right, this is a Virago single board computer being tested at the Massachusetts General Hospital. So we piggyback on the 200 MeV proton beams that are performing cancer treatments during the week and are often performing electronics parts testing over the weekends or on dedicated rooms, sort of segregated from the medical facility. So there's a number of these facilities that have cropped up over the last decade and a half, performing this type of work, especially for the commercial space industry. The value of testing at something like the NASA Space Radiation Lab on the far left, or the medical proton facilities, so that we can test a full board. There's complexities to that, both physically and logistically, but we can put a whole computer essentially in front of the beam and understand what it does, as long as we have the time and the dedication to do so. So that's a lot about parts and building up the basics of what our parts may do in a radiation beam. I want to show you a little bit about the effects on some of the non-volatile memories that are critical parts of space computing systems. So I spend a lot of my time doing flash memory testing. And so you're going to see sort of a flash focus, if you will, on this work. That's just one of the fields I've done a lot of my research in here at Goddard when I'm not working on flight missions. So most of the time, classically at NASA, when we are building data storage systems for space, we have been building something from scratch, buying space grade or sometimes even commercial memory, integrating a system, building a custom solid state recorder controller with an FPGA, delivering a board, putting it in a big brass box, flying in space. That's how we built the 10 terabyte data recorder for Roman Space Telescope, which you guys, I believe, saw being integrated if you were on the tour yesterday, as part of the command data handling system. But in order to do that, we need to understand what the flash memories themselves are going to do. So this was a test from a couple of years. I believe the testing was done in late 2022. On the left side, we see 3 different commercial, sort of state-of-the-art 3D NAND flash memories, all in the 512 gigabit class of die. Some of these have 16 die in a package, so up to a terabyte in a single little, postage stamp size device. While I won't go down the rabbit hole of what we're looking at here on the right, the point I want to get at is that we are characterizing bit cell behavior, understanding how a single bit is being affected by ionizing radiation. When we spend enough time at the test facility, we can build out a complex curve. We can understand the differences in how we operate the device and what the effect will be that leads us to something like n bit upsets per year in a particular environment. This is very low level characterization of how these systems behave. At that level, when we talk about single event effects, we're usually looking at bit upsets. Sometimes we see nuanced effects in some of these flash memories, like blocks, individual blocks that are inaccessible, even though the rest of the device behaves. We will see weird sequential or repetitive data errors, like every 100 bytes there's an upset, or every other page is inaccessible. We see sudden supply current changes that can be potentially destructive, but are usually just indicative of essentially an uncommanded operation at the device level. We will see reads, programs, and erases are sort of the fundamental operations of a NAND flash, and sometimes these will simply fail to complete or take longer than they should. And devices that just stop talking. are probably all of the most common SCEs when I talk about a NAND flash test. From a total ionizing dose standpoint, this is the cumulative effect. We see long-term data corruption. Eventually your bits are going to start wearing out, especially those that were programmed. Usually the weakest are going to start to fail over time if they're not refreshed periodically. We will see with NAND in particular that erasing suddenly starts to become the dominant effect. Because erasing requires higher voltage, there are higher voltage transistors within these flash devices that have thicker oxides and make them more susceptible to TID. So this is a vulnerability with NAND flash specifically. Not as prevalent well, it's not prevalent at all in something like an MRAM, an FRAM, or a ReRAM. Some of these technologies are much more resilient to radiation, except they still have all the surrounding CMOS circuitry, which can potentially be susceptible to your upsets and latch up themselves, even if the memory cells are not. And then long-term increases in supply current, and eventually the memory fails. So this is piece part level. And we do all that because it's informative to our system design. So we are either characterizing things like, let's see here. Upper left, we have different read offset voltages. These are designed to give us these are commercial features to increase the lifetime of the device, improve retention and endurance specs of the device. But we can also use it because we have knowledge that single event upsets can only push our data one direction. So if we shift the read offset voltage another way, we can build a essentially customizable tolerance to radiation here. In the middle, we have some information about operating these devices in single level cell versus multi-level cell, where we cram more than one bit into an individual floating gate transistor. We can explore pattern dependencies on these error mechanisms. This is looking at some of the tail effects of how far we shift a programmed cell versus an erased cell. The point being, we can optimize a hardware system for fewer bit errors by having this low-level data. But we also have high-level effects that aren't related to the bit cells themselves. So on the left here, I'm showing, it's just a cutout from a text file. It's a large portion of a single block where all the data is zeroed out instead of being these specific values that I'm looking for. We're getting all zeros, which is not because the bit cells themselves have been zeroed out, but because the control circuitry surrounding it is misbehaving. We have weird effects where the static device suddenly starts drawing a lot of current, like it's operating when it shouldn't be. On the right side, we have failures of reading and writing commands that shouldn't have happened. And so what I'm getting at here is that on the previous couple of slides, we talked about bit cell errors. Well, what I haven't addressed is that a lot of these memories have very strong error detection and correction, even for terrestrial applications. The flash memory in your phone is probably triple level cell, which means you're cramming 8 analog levels into one transistor. There's going to be a lot of errors. Some of these devices are rated up to 1% raw bit error rate correctability. And that makes them more susceptible to ionizing radiation, but it also means you have a ton of resiliency built in for those one-off galactic cosmic rays that do come through. What it doesn't mean, though, is that you have any ability to recover from something like a block level failure, a SEPI, a single functional interrupter, any of these system level effects that really aren't relevant to the terrestrial application. So the upsets in that control circuitry are something that you're not going to see in your laptop or your cell phones. The memories and the architectures are not built to be resilient to that, but that's what we do see in space. And that is really what drives our availability and our reliability of these systems. So a lot of that information then becomes informative. I talked about what was the previous title here, informative to system design. We also test data that's informative to operations for our systems that are using these memories. And so these are a couple slides cut out of a different presentation here, where we explored specifically targeting the radiation during operational phases of these memories. So only irradiating during an erase, for example, or only irradiating during a program, and understanding how the behavior of the system varied based on when we cause these effects and how we can operate in a manner to reduce, the end result of this is these charts. We have, depending on the duty cycle, some of these, we have data lost events dominating versus data preserved events. A data preserved event meaning I can recover from it. Everything was saved in the memory just fine. As long as I reset, it's there. And a data lost event meaning I thought I was programming data in all day, and I realized later, oops, it wasn't saving anything. All of that's based on when we do things like proactive power cycling to recover from transparent errors. And then, yeah, just like I started my here. One of the common mitigations we see is, well, I know this part is going to have weird error modes. What if I just reset it once a day or every other day? And while that's a common mitigation, it doesn't stop the underlying effect from happening. All it does is reduce the criticality of the effect. And so we can do some complex simulations here to really understand what the system level effect will be in terms of the amount of data we lose versus how often we have downtime to recycle our system. And we can also drive our architecture. We can have test data that's informative to the architecture here. And so this was, this is some complex analyses here. I won't go into too much, but I'd be happy to share the underlying papers with anybody that wants to email me. And we did a probabilistic system analysis showing how different EDAC architectures and the distribution of some of the EDAC code words, for example, across multiple die and multiple systems can lead to a more resilient architecture. This is taking the piece part data, building a more resilient system. There's a lot of tools out there to help you with that process. SEAM is something that Goddard and Vanderbilt have been working on recently. This is model-based systems engineering software. And really on the right here is just showing you goal structured notation of taking that low-level device requirement and flowing it all the way up to a resilient system. But that's piece part testing. That's sort of the old way of doing it. And what we see increasingly is folks wanting to fly something like a commercial or an industrial or an enterprise solid state drive. If we built this huge box for Roman that can store 10 terabytes, but I can buy a 10 terabyte drive off the shelf now, what's the difference? What's the trade-off? You can imagine that the testing complexity is very different here. And in some ways, it's a far more complex test to test an entire drive assembly. And in other ways, it's much, much simpler only because there's so much less we can do with it. So on the right here, so on the left, we have a traditional NAND flash piece part in front of, that's probably at Lawrence Berkeley National Lab doing device level irradiations. And on the right, looks like it's an Exascend solid state drive at the NASA Space Radiation Lab, where we have a little bit high energy we can actually penetrate through. And so we are irradiated here, not just the NAND arrays themselves, but every component on this device, and then doing some sub-irradiations where we look at individual components and their behavior and interactions. So this was testing, let's see, this is just to show you some stuff I did this summer. This is very high level SEE testing. And what I mean is this is putting that SSD in front of the beam and seeing what happens. And so there's only so much data fidelity you can get in if you're not directly tied into the manufacturers with some of their tool sets. So we see on the right here a long duration, by our standards, long duration test, meaning it lasted 19 minutes. And there are 8 events. You're looking at just a power supply current draw here, but what we can see are 8 events that were detected and autonomously recovered by our test setup. And what we end up with is not all of those charts showing bit cell fluctuations and changes in threshold voltage, but the number of parts we tested, well, I won't even get into the mechanics of what a threshold LET is, but we basically say the device worked until it didn't, and here's how many particles we put on until it just stopped working. And that may be the limit of the fidelity we have into the system, not what the bit cells are doing, but when did it stop talking and what did I have to do to recover operations? We can do the same thing for TID. There's a little bit of a nuanced test here, and this gets into where I mentioned it is very complex, and there are a lot of lurking threats to doing this type of system level tests. So the top chart there is power supply current of a solid state drive doing its reading, writing, while we irradiate it. We let that run, took it all the way up to 55 kilorad before the device failed. 55 kilorad probably doesn't mean much to most people in this room, but that is more than enough to survive really any LEO mission, even most missions in GEO or some of the Jovian missions when we incorporate the shielding present in our spacecraft. So meaning that's a very good result. But the bottom is the result of a secondary experiment we did for a completely unrelated reason, but we started turning it off and back on again during the testing, and we realized after only 16 kilorad, which is a much more important, much more critical level, we couldn't turn the thing back on again. So these are some of the weird effects that has nothing to do with NAND flash or non-volatile memory, but the device simply couldn't boot itself up. It could keep operating, but it couldn't start up from scratch. That's not necessarily part of the test flow I would have incorporated, with a tunnel focus on the memories themselves. Here's a question.
Yeah, so I was just asking, so a lot of the hardware manufacturers, they're running like error correction code, they make you turn it on. Is this running with error correction
Yes.
code on? Okay.
Yes.
There's a lot of accelerator work going into FPGAs right now,
Mhm.
especially with some AIs and the processing and recognition side. Have you been looking at the behaviors of FPGAs in this context?
Yeah, so I mean, we have folks doing, on this, let's see, when we were there in June and in September, we were looking at the AMD Versal devices, the ACABs, and we've also had a few different radiation tests, some of the AI accelerator devices.
Yeah.
And boy, that is a whole nother level of
That's-
taking the determinism of a,
Yeah.
you know, a voltage regulator and saying, I see it makes a voltage and it still makes a voltage at the end of the radiation test versus an AI accelerator and trying to understand the community, is still trying to wrap its hand around
there's-
how we characterize that kind of device and say
Yeah.
it's degrading versus it just stopped working. That
we're
that is an
gonna-
open field of research and yeah, and complicated. Again, when we talked about the commercially available drives, just some of the common error signatures to bring it up to the drive level here. A lot of times things suddenly become unresponsive. They're still plugged in, they're still drawing power, but I can't talk to it. I've seen these drives be locked into a read-only mode where they refuse to write data. As they are visible to the system, meaning the operating system can see it, it's there, but it won't do anything. We see sudden supply current changes that may or may not affect our operations. A marked decrease in our read or write speeds. Sometimes this is because sometimes this can be an artifact of the testing. I will caution that you've created so many errors in the device as part of your testing. But now it spends a lot of its time under the hood doing garbage collection and moving data from one block to another. We see changes in the device ID or the metadata being corrupted. From a total ionizing dose standpoint, again, at the drive level, we will see those degraded read-write speeds, long-term data corruption, increase in supply current, failure to boot, we just talked about, intervention failure to operate. And really the takeaway in red there is that none of these are expected by a commercial OS. The drive is not supposed to just stop working or pause or slow down or recover, but they may be poorly handled. And certainly that's a challenge for us trying to build a cheap off-the-shelf test vehicle for these parts too, is having something that can provide the same resiliency and characterization that we would have seen with our piece part level test that we can customize, and now having to build something OS based to test the drive is its own challenge just to do the testing. From an operational standpoint, just what I talked about there, if we're building our own test, the old way to test a piece part, we can characterize and recover from all these effects. We can build up all the data in the world that describes how radiation affects the memory. But when we're operating through that OS based world, often we'll see something, if it's on the end of a USB extender, fine, it turns itself off, it comes back on. Pretty robust, but when we're testing tied directly into the PCIe bus and something crashes, it'll often take the OS down with it. We will see drives suddenly unmount themselves, but we have to turn the whole computer off and back on, bring back power. We'll see partitions that disappear. The testing software may behave poorly when the drive suddenly has much higher latency than it did before. We will have drives that turn themselves on when they're supposed to be sleeping. That's sort of a test you might not think about as well as testing the device not doing anything and understanding when it starts to do stuff. And all those black box activities within the drive, I've had a lot of conversations with some of the manufacturers about this behavior, where we'll see remapping and rebuilding of metadata happening under the hood, and we actually just have to wait for some of these processes to play out before we can resume our testing, even though the device is behaving perfectly fine. In terms of error correction, I did also, one of the things we see is essentially no flipped bits. If you take one of these drives, plug it in, irradiate it, and expect to see a big text file change, you're not going to see that because of all the error correction built in, unless you have the hooks in to turn off that error correction and want to do that for part of your test. Otherwise, you're not going to see the flipped bits. You're going to see everything else that brings down your system and affects your availability and reliability. Do you have a question?
Yes. Is anybody working on building a formal taxonomy of these failure modes? Some of it you could potentially manage using bit or CBIT or, building tests. Is anybody working on a formal taxonomy?
I don't know that they're working on a formal taxonomy. That's a good question. There are definitely manufacturers working on not a radiation hardened SSD per se, but some of those wrappers around these devices that will attempt to detect, recover, and make this a little more transparent at the operating system level, sort of a box around the device. So there's a few different folks working on that, but maybe on the next slide, one of the challenges with these devices is as we get more complex, in the past, if we'll use a voltage regulator as an example, you could find one that was good enough. With the piece part NAND flash, you can find the part that's good enough in most cases to apply it. You might have to do some testing and maybe some mitigation, but we can find something that just happens to be good enough serendipitously. That has not been the case with solid state drives, and there are numerous parties out there performing testing of commercially available drives, and really there is not one out there that is it's good enough to apply. So I'm still looking for that as the starting point for some of these system designs. Yes.
I guess follow on maybe next level, like the previous presenter talked about the different classifications of software. You're talking about hardware reliability and how radiation can affect it. How do you see the mapping of the different classifications of software to multi-core architectures and things like that? Can we use multi-core architecture for Class A software? Well, that because the complexity goes up exponentially, so your reliability and the challenges you have, this is stuff way up.
Yeah, and we used to be able to operate in this environment where the software people could do the software thing and the hardware people could do the hardware thing, and I would make the part good enough. I think that's really this slide is what I was going to get at here. Is we could go through a parts list and figure out what parts were good enough and which parts needed to be tested, and eventually you get to the point where your part met the requirement and therefore the system would behave as you needed. And that's increasingly uncommon. And AI devices, really complex FPGAs that really aren't even FPGAs anymore is another one where we can't just say this part passes its test, therefore you should use it. It's all about the interplay with the software and the operations for a particular environment. What that means is not just tolerating an effect in the sense that you've filtered out a voltage glitch or something. It means having a distributed architecture where you have memories being stored in multiple locations. None of the EDAC is in one place, and you don't have all the memory, primary memory in another. You're able to operate through failures of individual devices. And so those are some of the more resilient designs that we've seen at a system architecture level, like, use the Roman solid state recorder as an example. That device can tolerate, I don't know if I should share the number, but a certain number of die completely failing. It doesn't matter what happens to the individual die, the NAND flash die, the system can tolerate through that. It's able to correct enough words that it can build this all together, just like a RAID array in a server farm or something. If one hard drive goes down, the whole thing can operate through it. So that's what I see from a hardware architectural standpoint. How that maps into software, I'm hoping that you guys can figure all of that out.
Okay, we've got time for one more question.
Yeah, I mean, I come from the automotive and my previous experience in industrial domain, right? So really, what happens in this domain is that the hardware vendor, right, that qualify hardware for automotive or industrial usage, right? So we do the failure mode analysis of hardware number of failures, like this one, and we'll define safety mechanisms in hardware that must be used in order to avoid or detect such failures, right? And the definition of these safety mechanisms would also be the source of requirements for the operating system. For example, if there is an ECC, memory protected ECC, then the OS must be able to handle the interrupt that would come if there is an exception that regard, if there is an ECC parity violation. So now my question is, wouldn't this model work also for the space? Like, having the OS, the requirement for the OS would be to functionally support, the safety mechanisms defined to avoid or detect such hardware level things.
I think so, and that's part of what we would do in a real thorough radiation hardness assurance program is understanding all of those vulnerable modes and how they are handled, whether that is by software or hardware mitigation. The places where I see this not working well are users that are taking entire systems off the shelf and even sometimes performing radiation testing, but they are performing the radiation testing in a way that was applicable in times past. So, I mean, I'll use a solid state drive, for example, because we keep talking about it. There's a temptation to take the drive, put in a radiation beam and do a single event latch up test only, put high temperature on it, potentially elevated voltage if you can, and you're really just screening out destructive effects. And that is how CMOS devices can be loosely approved for high-risk emissions. You're at least screening out all of the bad stuff that will kill the device. But what we see as the devices are complex systems of systems, you can't put the device in all of its operating modes where all of the internal devices are powered at the same time, do the kind of testing. And then potentially you're missing very obvious failure modes, like the mapping data in the drive being corrupted. That's a bit upset. It's normally a non-destructive SEE, but because of the way that affects the system, that it now can't find any of the data that's been mapped all over the drive, it fails in a truly destructive, from a mission standpoint. Even though it's not a destructive SCE that people like me would have thought of from a physical standpoint. And so communicating that to systems developers is very challenging, that it's not just the destructive SCE. In fact, that may be prevalent, but not the driving risk. It may be the way the errors are handled by the system. So having a thorough characterization of what those failure modes look like, even for an automotive or industrial system, because some of these are not, they were never considered in the design of the system, that it would have a failure of the serial bus. And so now we have to be able to understand at the OS level, whatever the larger architecture is, that there are going to be failure modes that when we're relying on an automotive or an industrial process, they're not considered at all. Well, we want to make this truly a space part. Ideally, you would think about all of that. But everything is moving towards faster. Let's go, let's test and iterate. So that's a real challenge to have that level of effort necessary.
Unfortunately, we run out of time. We do have 2 questions from virtual audience and I want to get to them. So the first one is, do you publish any of the test results and analysis? For example, Versal?
Yeah, absolutely.
All right, and where can we find those?
So most of that stuff gets, I mean, the Versal stuff is very new, so I'm not sure what's publicly available yet, but most of that gets published in the IEEE Transactions, Nuclear Sciences, TNS. That's sort of a journal of record, if you will, of radiation effects community.
Awesome. The last one is, what about large MRAM or non-volatile memory?
Yeah, MRAM is great. I mean, we've done a lot of MRAM testing. We looked at other folks in the community that are building large systems. We're not at a point where we have terabyte class MRAM devices. I keep hearing about this for a long time, but it brings us to a point where the bit cells themselves are not resilient, but now you really still need all that surrounding peripheral circuitry, because from a purely commercial MRAM standpoint, you may have latch up, something very basic like that in the CMOS that surrounds the device. And so if you're taking a robust process that has MRAM available and you're designing your own system, you can build a very robust memory chip doing that. If you are capitalizing on a commercial memory that uses one of these non-charge based memory architectures, wasn't designed for radiation tolerance in all of that peripheral circuitry. It's as hit or miss as any other technology.
Awesome. Thank you, Ted.
Thank you.
Anyone virtual, we're gonna take 15 minutes, and then for everyone here, there's coffee, pastries, and there's a sign-up sheet for the pizza lunch order, and make sure you